Shani Rodriguez. I'm a physics major and public health minor of the class of 2017, and I'm currently the greenhouse gas inventory intern at the Center for Sustainability. So in my role as a greenhouse gas inventory intern, it's my job to collect data from different departments on campus, as well as electricity usage and natural gas usage, to compile that into a national database calculator that in turn calculates how much carbon emissions in metric tons of CO2 that the college produces in 1 year. For the academic portion of my 450 internship with the center, I've been working with Dr. Ackerman on creating basic climate models using Python programming, which is the language that the physics department teaches here at Agnes Scott. I use Screencast-O-Matic in the next portion of my video to demonstrate my basic climate model, as well as some of the tools I use to create that. So take a look. So here is the code for my basic climate model. I've coded my model in Python because that's the programming language that the physics department teaches here at Agnes Scott. You can see here where I've evoked some packages that already exist in the Python language developed by other people, and where I've assigned my values here. So the main attraction, so to speak, of my program is this segment of code right here. And this is going to be the temperature approximation, as I've called it here, with two variable inputs, T, which will be the change in time, and TMP, which is the initial temperature that is input by the user. To create my basic climate model, I've used the textbook Climate Modeling and Differential Equations by Dr. James Walsh in the Math Department of Oberlin College. I really like this textbook because it gives a good breakdown of the initial equation it uses. So to start, here is the equation that I've used as the premise for my climate model, and I've rearranged it a little bit so that it can output the change in temperature here. So the equation as it stands is the energy balance equation, and Dr. Walsh credits it to Caper and Engler. And here it's saying that the heat capacity times the change in temperature over the change in time is equal to the solar radiation incident on the Earth per square meter times 1 minus the planetary albedo, which is the reflectivity of the Earth, minus some constant by the temperature to the fourth. In this textbook, Walsh gives an explanation for each of the variables in this equation, as well as the appropriate units to use for it. So T will be in Kelvin, and this will be the average temperature of the Earth. Little t, lowercase t, is years, and this is just time. R is the average heat capacity of the Earth, and that's in watt years per meter squared times Kelvin. And then Q is the solar radiation incident on the Earth per square meter, and that's in watt per meter squared. Alpha doesn't have any dimensions. It's a value used to represent how much potential the Earth has to reflect back solar radiation into the universe. And then omega is watts per meter squared times Kelvin to the fourth, which is the Stefan Boltzmann constant. Walsh also gives some values for the parameters in the equation, which I have used in my code, and the heat capacity is 2.912. The solar radiation is 342. The albedo here, alpha, is 0.3, but later Walsh gives an example of how to make the albedo, the reflectivity, dependent on temperature, because as you know, as global temperatures rise, the reflectivity of the Earth will change as ice glaciers are melting and more non-reflective land is being exposed. And then the Stefan Boltzmann constant, like I said, is constant everywhere. So it's 5.67 times 10 to the negative 8. So going back into my climate model, you can see that I've already input these values here into my main code. So going back to the textbook here, within this same first chapter in the exercises, Walsh shows how you can include the emissivity factor of the Earth's atmosphere into the equation. So that was not present in the first equation here. So essentially, by not including an emissivity factor here, we're saying that the emissivity of the Earth's atmosphere is completely perfect. It's 1. The factor is 1. Therefore, all of the incident solar radiation on the Earth is able to freely escape from the Earth's atmosphere and not get trapped back in. However, we understand the value of calculating greenhouse gas inventory is that we can calculate the college's carbon footprint, and therefore the amount of carbon emissions that our college produces every year. This directly affects, and not so much as maybe larger corporations because we are a small college, but this directly affects this emissivity value in the equation. And so I've actually included that in my climate model. So you can see that I've included the emissivity value here of 0.6, which means that 60% of the solar radiation that is reflected off of the Earth and back to the atmosphere will be able to pass into the universe. However, 40% of that solar radiation will get trapped back into the Earth's atmosphere and will contribute to heating up the global temperatures. And that value is in here in my loop. So continuing on, I mentioned that Walsh uses a temperature-dependent albedo function here that I actually wanted to include in my basic climate model because it makes it a little bit more complex. So this equation here shows that as the temperatures increase, the reflectivity will decrease. And I've included that equation right here in my loop. So in my reiterative method, the initial temperature that the user inputs will get looped through these equations. As each temperature passes through these equations, it will output a new temperature value that will be the y values of the output graph. So I will demonstrate this now. So I'll execute my cell, and I will input our change in time interval, which will give us our precision. And so for here, I'll input 0.3, which is not very precise. And I can input now a current accepted average global temperature in degrees Kelvin. And I said before that the equation takes temperature in Kelvin. However, the user will use something a little more standard like Celsius, and the program will actually convert into Kelvin by adding 273. In my run-ins of this, I've put in about 15 degrees Celsius, press enter, and here is the output graph. So the output graph shows that at time 0, which would be today, 2016, and over 8 years, the temperature of the Earth will increase about 1.1, 1.2. And because this is a basic climate model, it's not quite as accurate. The rest of the textbook that I use, however, shows examples of how you can add on to this program to make the climate model a little bit more complex and a little bit more accurate, because global temperature increases don't affect only emissivity or reflectivity. There are many other factors to consider. While there are places like the United States and places in Northern Europe that will enjoy lower winter mortality rates due to even 1 degree increase in global temperatures, places like Africa, Middle East, Asia, and the Global South, we can expect higher migration rates due to climate disasters. So you see, there are a lot of implications to creating these climate models, especially complex ones, that larger organizations like NASA create. It is my hope that future interns in the center will continue to make connections between sustainability and their respective majors and create project presentations like this one to showcase all that students can do to raise awareness around climate change. Now, it doesn't have to be a video, it can be a blog post, it can be anything, but we should continue to make our campus more proactive in fighting climate change.